YZB graphs. And we can define product Y cross Z. So let in simple undirected graphs, we have already mentioned that presentation of the vertex set and edge set will completely determine the graph. We don't even need to go back to the mapping definition. So let V vertex set of Y cross Z is a set Cartesian product of V vertex sets. This is set product. Set Cartesian product. And edge set is also given clearly. Now this is a Cartesian product of sets. So every element of this is an ordered pair of with first one coming from vertices of Y, the second one coming from the set of vertices of Z. So for this edge in this graph, it has to be between two ordered pairs, right? So we write it. So it's a set of two ordered pairs, U, V, X, Y, ordered pairs. This is the vertex in that.
Okay.
This is a set in this product. This requires that U is just Ux is an edge and Vy is an edge. Ux is the edge of Y, Vy is the edge of Z. And it is an and, so it's a conjunction. Ux is an edge of Y and Vy is an edge of Z. It seems easy. After we define the second one, third one, we will give lots of examples, a few examples, not lots. And another product, I'm going to denote it with this, and then we're going to argue that these are good notations, and the names we're going to give them are really good. I'm not going to use any one of the hundreds of papers published in the last year, which most of them got it all wrong, the name wrong. We will prove that as well. So let X and Y, Z be graphs, and let the vertex set is a set Cartesian product. And the edge set is, again, it's two elements in there. It's two subsets of two elements, each is an ordered pair. Don't be afraid of these things. It's actually, as soon as we see examples, it actually comes out very easily. So this requires, this direct means it's like we're going to take two real axes and then place them perpendicularly, and then for any fixed x, all possible y's are there, and for any fixed y, all possible x are there. That is why we use this symbolism. Now you can understand that it's going straight, horizontal and vertical. So this means that if u, x are equal, then dy must be an edge. Edge of the second graph. If Vy are equal, then Ux is an edge of the first graph.
I think this product is known as corona product.
What?
I think this product is known as corona product.
Corona?
Yeah.
This word?
No.
Corona.
Yes.
That is one of the bad names that I'm going to criticize. I haven't heard this yet.
Yes.
The first time I'm hearing from you, Muhammad. It's not a good idea. Some people call it box product.
Yes.
All very vulgar and incorrect. Let me tell you, I'm going to prove it now, soon. But before proving, we need another definition and a few examples. The strong product, they call it strong product in graph theory. This is a strong product of YZ is the union of these two. Namely, these edges are there and these edges are there. If they are not repeating. If they are repeating, then we take the union. This is called a strong product. We only consider these three. There are at least another 2, 3 of these many products in graph theory and lots of different morphisms. Now, let us see examples first, and then we want to argue what I just said. Those units are not correct. Anybody needs short of this? I will erase it, okay? So let us do some simple examples to understand these two products of graphs. And these are all new metric spaces constructed from known ones. Something like a knife. Okay, let us take y to be this graph. This is y. Let us take x to be this graph. Very simple, isn't it? Oh, no, z. And then we look at we draw the first and the second product. Now we need to mark the vertices first. So for this vertex, there are 2 there. So this one, first coordinate is this one, the second coordinate is those 2. Going up. And here there are 2 as well, and there are 2. It agrees because Cartesian product, number of elements is the product of the number of elements. So 2 times 3 is 6. So we have 6 vertices. If you label this as A, that as 1, then it's A1. That's A2, this is 2. This is B. This is 1, 2, then B1, B2. This is C, C1, C2. Going that way is no problem. It's A1, B1, C1. Oh, when I'm saying A1, this denotes A1. You can read it like that, right? Okay, what is that first product? There is an edge between these vertices and those vertices, and there is an edge between these as well. So those are edges. That one are edges. Is there an edge there between these two? No, because there is no edge that goes from here to here. So by our definition, there's no edge there. There's no edge there, and there's no edge there, no edge there. Because if there's an edge, that must be an edge to itself, and we didn't have it. Of course, if you have that, then there is an edge. But why don't we erase it? This means that the non-simple is also fine. And similarly, there is an edge there, and there is an edge there. No other. This is a cross. This is y that. You shouldn't really read it as a cross product. Many graph theorists call it cross product. And how about the other one? The second product this is your y, this is your z. Oh, I see. In the Euclidean plane, the first one is horizontal and the second one is vertical, and we just put it other way around, right? It doesn't matter, right? Does it matter? It matters when you consider whether z, y cross z is isomorphic to z cross y. When you consider that question, it matters. Otherwise, we just call this is horizontal, that one is vertical, no problem, right? It's in the Euclidean plane, the first R is horizontal, the second R is vertical, right? That's what I'm trying to explain. So there are 6 vertices. graph is more complicated, it's going to need a computer. Now, this one has, if
Box.
first component is equal, then we look at whether the second component are adjacent. If the second component is equal, then we look at the first component are adjacent or not. But that component, when this component is equal, that component gives you these three edges, right? Even without looking which one it is, but now if that component is equal, wait a minute, if that component is equal, it has to give these two edges. So this is the second product. And the third product is very easy now. You need to add the red edges. So that will be that one. If you erase the red edges, you get the second product. Now, without going through the set theory part, we want to state something. First is that in the category of undirected graphs, as I said, I'm going to use words to say it instead of introducing the symbols. No one is asking questions. Graphs. With morphisms as homomorphisms. Homomorphism as morphisms. This is a categorical product. This is a statement. What does it say? It says this. Let us consider this as the first graph. This is your y cross x. Y cross z. From y cross z, there is a homomorphism, which is actually a projection. Projection of all these edges going between those two sets of three vertices onto that edge. So there is a projection to the first component, y. Similarly, there is a projection to the second component, z. For example, these two edges are marked onto that, those two edges are marked onto that. And those two vertices matches this, those two vertices. It's just simply naturally onto natural projection. Then, for any given graph, x, and any homomorphism, in the category of undirected graphs with morphism, homomorphisms of morphisms, there is a unique isomorphism. This said that that product is categorical product in this category. This is the definition of a categorical product, right? These were projections on x any graph, and this is the homomorphism, that's homomorphism. Then there is a unique isomorphism. If this is satisfied, then we call this product categorical. Therefore, its proper name is categorical product or Cartesian categorical product of sets, category of sets, and the set mapping is called Cartesian product. So this name, proper name for this child, third, x is Cartesian or categorical product. In that category, therefore, the names cross, corona I have heard before, cross product, corona, anything else is not the proper not the name. We're not saying that it is wrong or incorrect. It is misnomer. A name given to a child which makes him, her, or her life sad. It's a misnomer. An inappropriate name, another way of saying in English is. Now let us consider the other product. Before considering the other product, let us consider in this diagram, in this illustration, partition given by these three sets. That's a contraction to this one, right? The image of this axis is this edge. Image of this axis is this edge. Image of that, those two vertices are not this one. Similarly. So this is the contraction marking. And similarly, it goes that way as well. By partitioning into these three vertex parts, then it is mapped onto this one. It's a contraction marking. So these two maps are natural projection in the category P1, P2, in the category of undirected graphs with morphisms, contraction markings. Now this mapping, this product is not category, even in that category. You will simply illustrate it. Let us consider this is K22. Complete graph of two. This is the part, this is the part. Or you can represent it in another way. K22. This K22, if you contract this edge, you get K3. That's one. If you contract those two edges, you get K2. So if you have a diagram must be correct, otherwise we're talking rubbish. Diagram is where is the diagram? You just you know the notation, so it's K22, K3. And then if you contract, then you have K2, K2, K3. This also there is a contraction of this inside. But here, not as much. Because it's a forward, it's not zero. So the contract in the category of undirected graph with contraction markings as morphisms, this product is not Cartesian. And that product can only be in this category. So this product is not Cartesian. Right. There must be other graphs examples as well. In its natural category of undirected graphs with morphisms contraction. Therefore, this product cannot be called Cartesian or categorical. Or to be. But it was called Cartesian. Of course, no graph theorists were able to call it categorical because they never considered this categorical. So they called it always Cartesian, which is not correct. Cartesian or categorical. It is not. And some people avoided this by calling this box product, which I think fine, but like giving a child name trash. This I don't like. I can suggest the name for this product, which is known in mathematics. The name is known in mathematics. It can be called direct product, because it's direct. My suggestion is direct, but no graph theorist is listening to me even after my paper is published. Doesn't matter. Let them make mistakes. I don't make mistakes. It can be called direct product. Direct in both ways. Now this is about products. I mean the Klapsar-Knauer monograph and Helm-Shetty monograph has a theorem which they categorical products in various different graph categories. What's the time now? Eh? Time. It's time already.
Yeah.
Yes, I see. This is about all I planned for today. So, any questions, discussions, or comments? Look all very easy, but you have to know that some of these are not really accepted by my colleagues yet. Yes.
I think there should be the product is u, y, and vx because we can inject this from the graph in the cross product.
In this one?
Yeah, I think it might be u, y, and
No.
vx.
No, because this ux is in the graph y. V and y are in graph z. So u and y cannot be adjacent.
So how we can?
Now this is let us explain this. So let us call this u v x y. If u v, now this vertex is, let us call this one actually reflect along the y axis. So this is ux, this one. This is uy,
Yes.
and this is vx, vy, wx, wy, all other pairs. So now uv are adjacent, and this is uv are adjacent, and x, y are adjacent, therefore this edge is there. uv are adjacent, but x is not adjacent to x, therefore this edge is not there. So this is correct.
So it means uy is an edge.
Eh?
Uy is an edge.
uv are adjacent in this graph, right? X, y are adjacent in that graph, so it's ux, vy are adjacent in the Cartesian product. Not this ux is not adjacent to that or that. It is adjacent only to this one. Because uv is an edge here, and xy is an edge there, so it's ux, vy is an edge by that definition. Have to be both. And in this one, it's more obvious because one of them is equal, the other one is adjacent. If you consider the adjacency between u and y, this u and y are in different graphs, so they cannot be adjacent. Similarly, v and x are in different graphs. This one is in y, this one is in z. The second coordinate is in z, and first coordinate is in y.
Thank you.
If you practice a few more, you immediately digest it. So don't worry. And please do those 2 questions. Any other question, comment, corrections? This Mila is should correct me.
I have another question.
Yes.
Co-prime. We have fx, I suppose fu, fv in y as well. But I think there should be a map that should project into ub into fu f1. In
No.
co-prime definition.
Comorphism definition is it's a mapping from x to y.
Yes.
But if there is an h there, its image must, its pre-image must be image.
So it should be under some map.
No. There could be a map, binary division there must be there, but may not be a map. The binary division from y to x could be, definitely exists. But mapping from y to x may not be. Because we are only assuming that this f is a mapping from x to y, which satisfies the condition that pre-image of every h there is an h here.
And
That's
the second one is that in the homomorphism, we arbitrarily we are there
Yes.
fixed.
Arbitrary UV, but if there is an h there, then its images of every h is image, is an h.
So if we are arbitrary, then what is the difference between endomorphism?
Endomorphism is a homomorphism from a graph to itself, but homomorphism is could be from a graph to different graph. It could not be surjective because it could be an embedding unit. But endomorphism is a homomorphism from graph to itself. It could be even embedding, because endomorphism doesn't necessarily have to be surjective. Good. Your question triggers some thought. So, for example, we have products now. If you have products in any mathematical category, if you have an object already given, then there is a question, right? There's a natural question. Can it be factorized? So if you are given any arbitrary graph, is there some 2 graphs so that this arbitrary graph is given an arbitrary graph x? How to decide there exists y and z so that x is equal to y cross z? One question. The other question about this one. That kind of question has not quite been studied yet. So you need to really know that mappings in the category of graphs are not well studied yet. This simply implies that you can do lots of PhDs in it. But I don't want to really suggest that someone should have more than 5 PhD per year in order to. It is not because some able people cannot handle that. What is the main problem of that? You need to think in long time term. After 10 years, your many PhD students who have done things in the same topic will be competing with each other for jobs. That's what I don't want to see. So you need to have, if you have lots of PhD, you need to get different topics, even different fields. That will be fine. And that will be very difficult for the supervisor. Okay. Thank you very much.